Welcome to Exnoesis, where the boundaries of understanding blur into the gentle hum of the cosmic night. Consider for a moment your own being, the vessel that carries your consciousness through this unfolding tapestry of reality. If we were to meticulously quantify your physical composition, a fascinating, yet perhaps somewhat humbling, picture emerges. For an individual weighing approximately 150 pounds or around 70 kilograms, the intricate dance of elements within that form you is largely comprised of the most common substances found throughout the cosmos. Roughly 45 kilograms of your total mass, a significant portion, is pure oxygen, the very breath of life, intertwined within the water and organic molecules that define your structure. Another 12 kilograms are carbon, the fundamental backbone of all known organic chemistry, forming the intricate chains and rings that give rise to the complexity of biological existence. Hydrogen accounts for approximately 7 kilograms, omnipresent in water and organic compounds, a fleeting partner in countless biochemical reactions. Nitrogen, essential for proteins and nucleic acids, contributes about 2 kilograms, while calcium, the architect of your skeletal framework and a vital signaling molecule, makes up a solid 1.5 kilograms. Phosphorus, a key component of DNA, RNA, and energy transfer molecules, adds around 700 grams, a hidden workhorse of cellular function. Beyond these major players, a myriad of other ingredients exist, present in smaller yet equally crucial quantities. Potassium, sulfur, sodium, chlorine, magnesium, iron, fluorine, zinc, copper, iodine, selenium, chromium, manganese, molybdenum, and trace elements like cobalt and vanadium, each performing specialized, often enzymatic, roles within the grand orchestra of your physiology. These elements, though diverse in their individual properties, collectively constitute the astounding complexity we recognize as a human being. When laid out in this precise, almost clinical manner, this list of chemical constituents might at first seem unremarkable. A collection of the most ordinary, ubiquitous chemical elements, nothing more, nothing less. It prompts a curious, almost disquieting thought. Is this truly all that we are? A carefully arranged, albeit highly sophisticated, assortment of atoms? Forgive the bluntness, but in this reductionist view there appears to be, quite literally, not an atom of anything inherently mysterious or profoundly unique. Just a configuration of elements from the periodic table, indistinguishable in their fundamental nature from the rocks beneath your feet or the distant stars. But pause. Is this truly the entire narrative? Or is there, perhaps, something more residing within you, within us all? Something that eludes the neat categorization of the periodic table? Something that, from a strictly scientific perspective, should not, or perhaps even cannot, exist as a mere collection of fundamental building blocks? Could you possibly harbor a quality, an essence, beyond the atoms and subatomic particles that meticulously construct your physical form? This question, to many, might sound like the premise of a sensationalized documentary, veering into the realm of the implausible. Yet allow me to elaborate, to illuminate the subtle, yet profound, distinction we instinctively make. Imagine, if you will, that you were to gather precisely the same chemical elements I just enumerated. The oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, and all the intricate trace elements, and place them into a large, unassuming bag. Should you then carry this bag through a bustling public square, it is highly improbable that anyone would afford you a second glance, let alone attach any particular significance to its contents. It would simply be a bag, perhaps a heavy one, but nothing more. Now, let us imagine a further step. You proceed to empty the contents of this bag onto the asphalt of that same public square. At most, you might receive a reprimand, perhaps even a fine, for littering, for discarding what appears to be nothing more than inert chemical waste in an inappropriate location. There is no intrinsic value, no inherent sacredness in this dispersed collection of elements. However, consider a different scenario. What if, instead of simply scattering these elements, you were to meticulously, precisely, and with immense care, begin to connect them, atom by atom, molecule by molecule, assembling them in a rigidly predefined order? You are, in essence, constructing a human being. At a certain critical juncture in this assembly process, a threshold would undeniably be crossed. Beyond this point, the nature of your endeavor fundamentally transforms. You would no longer be able to simply disassemble your creation to break it back down into its constituent parts at will. Why? Because if you were to attempt such an action, if you were to endeavor to reduce this meticulously organized collection of atoms back into a mere bag of chemical dust, you would, with absolute certainty, be immediately restrained, condemned, and quite possibly incarcerated for many, many years. This thought experiment, as vivid as it might be, underscores a profound truth. At some undefinable point, this scattered collection of chemical trash, this agglomeration of atoms, inexplicably acquires a new emergent property. A property that we as a society not only deem to be of immense, indeed almost sacred value, but one that we are prepared to protect with the utmost rigor and at any cost. This inherent value, this perceived sacredness, is not readily apparent in the isolated atoms themselves. It only manifests when they are arranged in a particular, complex, and dynamic configuration. If this example strikes you as overly imaginative or leaning too heavily into the fantastical, let us ground ourselves in a more concrete, widely accepted reality. Consider the legal frameworks surrounding abortion in many nations across the globe. In these societies, the termination of a pregnancy without specific medical indications is permitted only up to a strictly defined legal threshold. This means that, from the perspective of society and its laws, at a particular moment in time, a nascent collection of atoms within a woman's body ceases to be merely a collection of atoms. It transitions, legally and morally, into something possessing that very new, invaluable, and inviolable property. This shift from inert matter to something deserving of protection is a testament to our collective, though often unspoken, acknowledgement of an emergent quality that transcends mere physical composition. This fundamental premise extends to our entire understanding of natural human rights. The very concept of a right to life, for instance, inherently contains the philosophical presupposition that, to borrow from the profound insights of Immanuel Kant, there resides within each individual something transcendental, something that is fundamentally greater than, and perhaps even distinct from, the simple matter from which your physical body is constructed. It speaks to an essence that cannot be fully captured or explained by a mere summation of atomic interactions. Yet, our deepest insights into particle physics, the most granular understanding of the universe's building blocks, suggest a different narrative. These insights tell us that if every single atom in your body were to be precisely replaced by another identical atom, you would, in essence, remain the same person. For you, subjectively, nothing would have changed. You would perceive no alteration in your sense of self, your I. If this notion seems fantastical or counterintuitive, it is, in fact, a process that is literally and constantly unfolding within your body every single moment of your existence. Back in 1954, based on groundbreaking experiments utilizing radioisotopes to track the movement of chemical elements both within and outside the human organism, nuclear physicist Paul C. Aebersold shared a truly astonishing conclusion. His research indicated that an astounding 98% of the atoms in the human body are replaced and renewed each year. Think about the profound implications of this. Throughout your lifetime, your physical body, in its entirety, undergoes multiple, complete renewals of its most fundamental building blocks. These atomic components are so remarkably interchangeable that, statistically speaking, there are atoms circulating within your body right now that, at some point in history, were integral parts of the brain of Isaac Newton. Or perhaps a dinosaur. Or a distant star. The atoms themselves are ceaselessly recycled, borrowed from the universe, and returned to it. This constant, radical physical transformation presents a deep philosophical conundrum. How can we possibly account for the unwavering, persistent sensation of being the same continuous individual throughout a lifetime, given that your entire physical foundation is in a state of perpetual flux? Your original body, the one you were born with, is, quite literally, undergoing a process of continuous dissolution and rebirth. It is, in a very real sense, experiencing a slow, molecular death as its components are exchanged. And yet, your inner self, your unique identity, your subjective experience of you, seems to endure, seemingly untouched by this relentless cellular and atomic turnover. For many religious traditions and spiritual belief systems, this paradox poses no significant challenge. They offer a remarkably straightforward explanation: the presence of a soul. As articulated by sources such as Wikipedia, the soul is often described as an immaterial essence, an underlying spiritual core that encompasses an individual's unique identity, personality, memories, and consciousness. It is, by this definition, an entity conceived to be capable of surviving the death and disintegration of the physical body, thus providing a continuous thread of selfhood independent of transient material forms. But does modern science simply dismiss such notions outright? What, indeed, can the scientific method, with its reliance on empirical evidence and verifiable observations, truly say about such profound and elusive questions? Recently, I immersed myself in the latest work by German theoretical physicist, philosopher of science, and expert in quantum gravity, Sabine Hossenfelder. Her book, which is not yet available in English under an official title, translates approximately to Existential Physics, a scientist's guide to life's biggest questions. The title itself, Existential Physics, serves as a potent hint, suggesting a daring foray by a physicist into the ancient, enduring queries of philosophy. One might naturally agree that to hear such profound contemplations articulated from the perspective of a seasoned physicist, rather than solely from a pure philosopher or theologian, carries a unique weight and fascination. The scientific rigor, combined with a willingness to grapple with the unknown, creates a compelling intellectual space. And what can be said about her approach? She navigates these complex territories with a captivating blend of insight and audacity. Immediately upon its publication in mid-2022, the book garnered widespread acclaim, hailed by many, among other accolades, as a beacon of clarity and sound reasoning. I have, in the past, produced content exploring some of the ideas from another of her influential books, Lost in Math: How Beauty Leads Physics Astray, or, in its localized title, Ugly Universe. In that discussion, I touched upon the critical issue of how scientists who neglect the philosophy of science inadvertently undermine the very authority of science itself, and, in doing so, lead research down unproductive, dead-end paths. Existential physics can, in many respects, be understood as a natural continuation, an evolution of these earlier themes. Hossenfelder emerges as a formidable intellectual figure, coolly analytical, refreshingly audacious, and unapologetically direct. A true embodiment of German precision and intellectual honesty. She is not one to shy away from challenging conventional wisdom or exposing intellectual vulnerabilities. I wholeheartedly recommend her work. And tonight, as is our custom, we will embark upon a contemplative journey with Hossenfelder as our guide, delving into her profound insights. What she reveals is that a vast array of concepts that, on the surface, might appear unscientific or simply absurd, are, in fact, entirely compatible with contemporary scientific understanding. And perhaps more surprisingly, many of these seemingly outlandish ideas possess a surprising degree of underlying sense and coherence. But enough of books, you might be thinking, as if there were no other forms of intellectual engagement in the world. Let us instead turn our attention to one of the most compelling and essential warnings that Hossenfelder explicitly includes in Existential Physics. This disclaimer, one that will resonate deeply with regular viewers of this channel, is itself a piece of profound philosophy. She writes with characteristic forthrightness that her book might be a danger to the reader's mental health, and further that one ought to give serious consideration to whether or not to even begin reading it, because, as she starkly puts it, some things cannot be unlearned. You might at this juncture be tempted to dismiss this as mere hyperbole, a clever rhetorical flourish designed to inject a sense of thrilling drama into the ostensibly dry realm of theoretical physics. A fair initial assessment, perhaps. And Hossenfelder herself, with her unwavering honesty, addresses this potential skepticism head-on. Listen, we all know I want this book to sell well, so why pretend that I don't? She acknowledges the commercial realities, but then she pivots to the core of her genuine concern. The main reason I make this warning is that I am genuinely worried that this publication might negatively affect the mental health of some readers. This is not a casual remark. She continues, recounting instances where individuals have reached out to her. From time to time, someone contacts me and writes that they stumbled upon one of my essays and now don't know how to live anymore. They seem genuinely distressed. Indeed, some scientific facts, when confronted without intellectual preparation or emotional resilience, can be profoundly difficult to internalize, to fully process and integrate into one's worldview. And what complicates this further, she laments, is that there are no psychologists who could help here. I know this from my own experience. This speaks to the unique existential challenges posed by certain scientific revelations, challenges that conventional psychological frameworks may not be equipped to address. Let us now gently transition into what Hossenfelder introduces as Chapter 1, Thresholds of the Unknowable. She begins with a statement that immediately draws us into the cosmic sublime. The greatest mystery of the universe is supermassive black holes. A claim that, while bold, resonates with the profound awe these enigmatic objects inspire. No one, she asserts, truly comprehends their genesis, their origin point in the cosmic tapestry. To illustrate their monumental scale, she cites one of the largest black holes discovered to date, TON 618. The diameter of this colossal entity's event horizon, the point of no return beyond which nothing, not even light, can escape, is a staggering 1,000 times greater than the distance from the Earth to our Sun. To grasp this immensity, imagine our solar system. If we were to define its outer boundary by the orbit of Neptune, the most distant planet, then ton 618 would engulf our entire solar system not just once, but 17 times over. Its gravitational maw is truly incomprehensible. To further paint a picture of its terrifying grandeur, Hossenfelder offers a chilling thought experiment. An astronaut intrepid enough to cross the event horizon of ton 618 would, astonishingly, remain alive for an additional 4 days. 4 full days of relentless, accelerating descent, a journey into the abyss, before finally reaching its central singularity, the point where its unimaginable mass, equivalent to 40 billion solar masses, is concentrated. This, she concedes, is undeniably impressive. Black holes are, indeed, objects of profound wonder and scientific fascination, but, she asks, where exactly does the fundamental enigma lie? The mystery, she explains, is this. The image we possess of ton 618 as it appears to us now is a snapshot from over 10 billion years ago. This means we are observing it as it existed at the very dawn of our universe, in its infancy, and astronomers are utterly perplexed, unable to reconcile how, in such a comparatively brief cosmic timescale, this behemoth could have possibly grown to such a gargantuan size. According to the prevailing cosmological models of our day, supermassive black holes simply could not have had enough time to form and accumulate such immense mass within that early constricted period of universal evolution. And yet, the perplexing observations continue to escalate. If the event horizon of ton 618, in comparison to Neptune's orbit, is already staggering, then consider the hypothetical, even more mind-boggling scale of a black hole known as Phoenix A. Its mass is estimated to be on the order of 100 billion solar masses, possibly even more. This transcends the very definition of a supermassive black hole. For such colossal entities, a new classification has been proposed: stupendous large black hole. These discoveries fundamentally challenge our assumptions. This raises a deeply unsettling yet intellectually invigorating question. How thoroughly, how accurately do we truly comprehend the universe's past? And how well do we genuinely understand the fundamental laws that governed it? Did the past truly unfold in the manner we currently envision? All available data consistently point to our universe being approximately 13.8 billion years old. And according to our current understanding, all the known laws of physics, in their familiar and consistent forms, are believed to have begun operating within the first fleeting moments immediately following the Big Bang, in less than a single second. Of course, the most parsimonious explanation, the one favored by scientific caution, is that we simply do not yet fully comprehend the intricate mechanisms behind the formation of supermassive black holes. Our models are incomplete, our understanding still nascent. But Hossenfelder, ever the provocateur of thought, extends the inquiry further. Is it conceivable that, in the distant past, different laws of physics might have been in effect? Laws that would have permitted these cosmic monsters to form with such rapidity? Or, to pose an even more radical possibility, what if our current calculations, which yield an age of 13.8 billion years for the universe, are themselves based on incomplete or subtly flawed assumptions? What if the universe is, in actuality, unimaginably older, perhaps 100 trillion years old, or even more? This is, admittedly, an exceedingly bold conjecture, a profound leap beyond our current empirical footing. But the honest, scientific answer, Hossenfelder reminds us, is simply no one knows. The notion of the fundamental laws of nature themselves undergoing change is something we have never, in the entirety of human observation, directly witnessed. Yet, the absence of observation does not inherently equate to an impossibility of occurrence. As Sabine Hossenfelder astutely observes, it is, quote, to come up with mathematical laws that would look indistinguishable from the currently confirmed ones, but which would blow up the solar system tomorrow. Meaning, it is hard to conceive of an alternative set of laws that would appear to function identically to our current understanding today, only to dramatically diverge in the future. Not that anything speaks in favor of this, she clarifies, but nothing speaks against it either. This highlights a profound limitation. We cannot, by any means currently available to us, conduct experiments to verify the exact laws of physics that were operational in the deep past. It is, quite simply, an impossibility. We are compelled, therefore, to infer. We might, for example, confidently state that, according to the laws of physics known to us today, light from a particular distant galaxy traveled for 7 billion years to reach our telescopes. But how can we definitively ascertain that, say, 6 billion years ago, the speed of light wasn't, for instance, a mere 2 kilometers per hour? The stark answer is, we cannot. Physicists, in their rigorous pursuit of understanding, are forced to operate within the confines of what is currently known and verifiable. They take the laws that are established in the present, laws derived from the comparatively brief span of human existence and experimentation, and on that basis, extrapolate backwards into the past. This approach is entirely consistent with the scientific method, a pragmatic necessity. But does this strict adherence to scientific methodology truly imply that the laws of nature that govern our present, and upon which all our intricate calculations are based, were invariably the same in the past? Or that they will assuredly remain unchanged in the future? Hossenfelder's profound insight is to state unequivocally, no, it does not mean that. This, she argues, is nothing less than a question of belief. It touches upon a long-standing philosophical problem, elegantly articulated by David Hume centuries ago, known as the problem of induction. This is a concept I have, in fact, explored in a previous discussion. In essence, the problem of induction centers on the inherent impossibility of definitively predicting that nothing unforeseen or unpredictable will ever occur. We assume, based on past experience, that the sun will rise tomorrow. We assume that the laws of physics will continue to hold. But this assumption is, at its core, an act of faith, however empirically supported. There is no logical necessity, no absolute guarantee that the future will mirror the past. Hossenfelder recounts her own encounter with this foundational philosophical dilemma. When I, as a student, first learned about Hume's problem of induction, I was puzzled. I felt like someone had pulled the rug of reality out from under my feet, revealing a vast, disorienting truth beneath. The profound implications of this revelation, the realization that our entire edifice of scientific understanding rests upon an unproven, albeit highly successful assumption, can indeed be unsettling. It fundamentally alters one's initial reaction to news stories, such as the unexpected acceleration of Earth's rotation, with scientists scrambling for explanations. The thought that the world might be fundamentally inexplicable, that it could harbor an element of irreducible chaos, a chaotic disregard for our carefully constructed presumptions, is a deeply unsettling one. It feels, to many, simply unbearable. It's a curious phenomenon, often cited as a demonstration of humanity's inherent philosophical bent. If you navigate Wikipedia by continually clicking on the first link in each article, excluding parenthetical notes or links to disambiguation pages, you will, in approximately 97% of cases, eventually arrive at an article related to philosophy. This informal observation suggests that philosophy, in a profound sense, represents the ultimate frontier of our knowledge, the point where our most rigorous inquiries eventually lead us. And the scientific method, for all its unparalleled power, is no exception to this rule. Does the scientific method work? Yes, undeniably, it works. Why it works, however, remains, in the final analysis, something we do not fully comprehend. And precisely because we do not fully grasp the underlying reasons for its efficacy, we cannot be absolutely certain that it will continue to function in the same predictable manner indefinitely. Sabine Hossenfelder reminds us that what we call science, the understanding of the limits of science, is always fluid. Consider Sir Isaac Newton, an intellectual titan widely regarded as the foundational figure of modern physics. In his era, his very name was almost synonymous with the word quote, science, an embodiment of rational inquiry. Yet, concurrently, Newton dedicated a significant portion of his illustrious career not to what we would recognize as physics, but to the arcane pursuit of alchemy. For 30 years of his life, he was deeply immersed in alchemical studies, his surviving notes on the subject encompassing over 1 million words. To put this into perspective, a typical novel of moderate length contains approximately 80,000 words. Newton amassed an enormous and, by all accounts, arguably the finest alchemical library in the world. He spent 3 decades of his life in fervent pursuit of the mythical philosopher's stone, an elusive substance believed to prolong life and transmute base metals into gold. And crucially, he viewed this alchemical quest as being no different in its fundamental nature or scientific validity from his groundbreaking investigations into the laws of gravity. This historical fact eloquently demonstrates the shifting intellectual sands upon which our definitions of science are built. So in succinct terms, what, according to Sabine Hossenfelder's contemporary understanding, constitutes science? She defines it thus: science is the search for useful descriptions of nature. The emphasis here lies on useful. By useful, she clarifies, she means descriptions that enable us to formulate accurate predictions for novel experiments, or that provide quantitative explanations for observations that have already been made. And there's a further crucial refinement to this definition. The simpler the explanation, the more useful it is. This elegantly encapsulates the principle of parsimony, or Occam's razor, a guiding tenet in scientific inquiry. Returning then to the tantalizing possibility of fundamental changes in the laws of nature, a particular hypothesis comes to mind: the omphalos hypothesis. This intriguing idea, proposed in the mid-19th century, attempts to reconcile existing scientific data, which strongly indicate an ancient Earth and universe, with interpretations of sacred texts, suggesting a much more recent creation, perhaps only a few thousand years ago. The hypothesis posits that God, or a divine creator, brought the universe into existence a mere few millennia ago, but engineered it in such a way that it bears all the intricate, convincing hallmarks and traces of being far, far older. It's a universe, in this view, created with an appearance of antiquity. To this, the renowned philosopher Bertrand Russell famously retorted with his own 5-minute hypothesis. His cutting rejoinder questioned the arbitrary nature of the omphalos hypothesis, asking, in essence, why be so modest? Why not, he suggested, postulate that the entire universe, complete with all our memories, all historical records, and all geological and astronomical evidence of an ancient past, simply sprang into existence from nothing a mere 5 minutes ago? Russell's point was to highlight the unfalsifiable nature of such claims, and the epistemological limits of our ability to definitively distinguish between a genuinely ancient reality and a recently created, yet perfectly simulated ancient reality. And yet, despite the philosophical challenges, could it be that our universe is indeed not 13.8 billion years old, but only a few thousand years old? This provocative question was addressed with remarkable clarity by British physicist Tim Palmer, whom Hossenfelder interviewed for her book. Palmer, when asked if he was religious, responded with a categorical no. However, he then proceeded to engage with the question in a deeply thoughtful manner. So I tried to ponder, is it possible to imagine a situation where such a belief that God created the universe 6,000 years ago would not be foolish and would not completely contradict everything we understand in science? Palmer then dives into the very essence of creation. What does it actually mean to create? What does it mean, for instance, to create an atom according to modern scientific understanding? His answer is striking. It literally means nothing, because, at present, all that science can definitively state about atoms is to describe, using sophisticated mathematical equations, what atoms do. Mathematics provides us with the algorithms, the interactions, the behaviors. But mathematics does not fundamentally tell us what an atom corbel in terms of its intrinsic nature or substance. From the perspective of fundamental science, the real world and its mathematical description are, in a profound sense, indistinguishable. It's akin to the often heard analogy that a map and the territory it describes are one and the same. What, then, do we truly imply by the word creation? Let us consider the creation of atoms. What are atoms? Well, as Palmer reiterates, all science can currently offer is that we can describe atoms using equations. We possess mathematical laws, and whatever you desire to know about an atom, these equations will reveal its actions and interactions. But mathematics, crucially, will not tell you what an atom fundamentally was. Is an atom merely mathematics itself? Is mathematics all that fundamentally exists? Or is there something else, some underlying substance or essence that confers realness upon matter, something that currently lies beyond the purview of the modern scientific canon? The answer to this profound question, Palmer concludes, is simply, nobody knows. Stephen Hawking, in his seminal work, A Brief History of Time, From the Big Bang to Black Holes, famously posed a related, equally penetrating question. What is it that breathes fire into the equations and makes a universe for them to describe? This query hints at a deep intuition held by many. Tim Palmer, and intuitively it's hard to disagree, suggests that there is probably something else in the universe around us that is not just mathematics. Of course, one might hold a different perspective, such as that of physicist Max Tegmark, who boldly asserts that the universe is literally mathematics. A perfectly valid, if equally profound, philosophical stance. But if you, like Palmer, don't subscribe to the universe as pure math view, then his line of reasoning continues. I'm not trying to advocate for this, but you could say that God created the universe through mathematical methods, and this mathematics describes how dust clouds gather and heat up to such an extent that nuclear fusion begins to generate energy, elements, and so on. All of this is just mathematics. This paints a picture of a universe unfolding according to elegant, preordained mathematical principles. And then, Palmer provocatively continues, 6,000 years ago, God got bored with this and said, "This is a bit boring. Now I'm going to make something real," waved a magic wand. And at that moment, real things appeared. This is Palmer's evocative way of suggesting a moment where, as he puts it, mathematics, as it were, became flesh. He then poses the critical question, can science disprove this version? How would science, operating purely within the realm of mathematical descriptions, differentiate between a universe that has always been real and one where the mathematical framework suddenly gained a physical instantiation 6,000 years ago. And therein lies the crux of his argument. Such a myth of creation, of everything emerging from mathematics 6,000 years ago, is not something anti-scientific. And therefore, Tim Palmer proposes the term ascientific. Ascientific is a crucial distinction. It doesn't mean unscientific or anti-scientific. Rather, it denotes concepts that exist parallel to science, outside its current capacity for verification or refutation. Because, as Palmer emphasizes, science simply has nothing to say about this, at least science in its modern form. There are indeed profound aspects of existence about which we are truly deeply ignorant, and this is one of them. The fundamental question of whether mathematics is merely a tool for describing the world, or if it is, in fact, the world itself, remains. We can argue about this, Palmer notes, but from a scientific point of view, we can say nothing about it. And if we, as scientists and thinkers, can identify and, crucially, acknowledge this boundary between scientific and ascientific hypotheses, then we can not only be, quote, more precise and bolder in our reasoning, but also, and perhaps more importantly, more likely to understand if we are capable of shifting that boundary a little. It is in recognizing the limits of our knowledge that we often find the greatest opportunities for its expansion. Let us now gently drift into Chapter 2, Can the Universe Think? The very phrasing is designed to evoke a sense of quiet wonder and perhaps a touch of intellectual vertigo. According to the most recent astronomical observations, our universe is home to a staggering number of galaxies, conservatively estimated at no fewer than 200 billion. These galaxies are not uniformly distributed throughout the vastness of space. Instead, under the inexorable influence of gravity, they cluster together, forming intricate groupings which, in turn, are interconnected by immense, filamentous strands of galaxies. These cosmic filaments can stretch for hundreds of millions of light-years, creating a vast, interconnected network. This immense, if you will, cosmic web bears an astonishing, almost uncanny resemblance to the complex neural networks within a human brain. This striking similarity was not lost on researchers. In a study conducted in 2020, astrophysicist Franco Vazza and neurobiologist Alberto Folletti undertook a quantitative comparison. They meticulously calculated the number of structures of varying sizes contained within both the human brain and the cosmic web. The results, as they reported, revealed a, quote, striking resemblance, a quote that truly captures the imagination. This leads to a profoundly speculative, yet irresistibly intriguing question. Could the universe itself be a colossal thinking entity, with our own galaxy merely one minuscule neuron within its unimaginably vast cerebral architecture? Hossenfelder, with her characteristic blend of scientific rigor and open-minded speculation, acknowledges the immediate, seemingly insurmountable physical hurdles to such a notion. On one hand, she explains, this idea appears to fundamentally contradict the established laws of physics. The universe is immense, almost inconceivably vast. And, due to the fundamental limitation of the speed of light, it would take hundreds of millions of years for a signal to traverse the distance between one galaxy and another. Given that the universe, since its inception, has existed for approximately 14 billion years, it is highly improbable that it could have engaged in much thought or information exchange in its lifetime. The universe, in its entirety, might have managed no more than 1,000 such exchanges between its closest neurons, a paltry sum compared to the billions of interactions our own brain processes in a mere 3 minutes. Moreover, the universe is not static. It is perpetually expanding, a process that continuously stretches these galactic connections, effectively diminishing its capacity to form and maintain rapid, intricate internal communications. This, then, represents the formidable challenge to the cosmic brain hypothesis from a conventional physical standpoint. But then, Hossenfelder, ever the explorer of theoretical frontiers, introduces a fascinating counter-argument, a speculative twist that dramatically reconfigures the possibilities. On the other hand, she writes, the universe might be permeated by a network of tiny wormholes connecting distant regions of the universe. If these hypothetical wormholes, these shortcuts through space-time, were indeed to exist, then signals from far-flung corners of the cosmos could potentially be transmitted almost instantaneously, bypassing the otherwise prohibitive limitations imposed by the speed of light and vast distances. These connections, she explains, would be far too diminutive for us, or even for elementary particles, to physically traverse. Their diameter would be on the order of merely 10 to the minus 35th power meters, an incomprehensibly small scale. Yet despite their minuteness, they would intimately intertwine the very geometry of the universe with its underlying structure. And, critically, there would be an astronomical number of such connections. Physicists Fatema Markopoulou and Lee Smolin, in their bold theoretical explorations, have estimated that in our universe there could be approximately 10 to the power of 360 such connections. To place this into astonishing perspective, the human brain, with all its intricate complexity, contains only about 10 to the power of 15 connections, synapses. The sheer magnitude of these hypothetical cosmic wormholes is almost beyond comprehension. And crucially, because these connections by their very nature would be non-local, meaning they inherently ignore distance, the ongoing expansion of the universe would become largely irrelevant to their communicative capacity. Hossenfelder, grounded in scientific caution, is quick to temper her speculation. I don't have particular reasons to believe that these non-local connections actually exist, or that, if they did exist, they would truly allow the universe to think. Her integrity as a scientist shines through here. But, she adds, with a characteristic openness to possibility, I also cannot rule out such a possibility, however crazy it may sound. Her concluding thought on this mind-bending hypothesis is particularly profound. The idea that the universe is intelligent is compatible with everything we currently know. This statement is not an endorsement, but an invitation to consider the boundaries of our current knowledge and the vast, unexplored territories of the possible. The immediate, often dismissive, reaction to such a question, can the universe think? Does the universe possess consciousness? Is typically one of incredulity. What utter nonsense, one might think. No rational person asks such absurd questions. It's simply preposterous. Yet the critical point Hossenfelder highlights is that these are, in fact, profoundly important questions. And here's why. There exists a pervasive, deeply challenging phenomenon in philosophy of mind known as the explanatory gap. Allow me to illustrate its core dilemma. You possess, with absolute certainty, the experience of consciousness. You know, beyond any shadow of a doubt, that you have qualia, the subjective, phenomenal, qualitative experiences of feeling, seeing, hearing, tasting, and touching. You have a palpable sense of your own self, an unmistakable experience of your individual I. Yes, indeed. This is one of my favorite topics, and I recognize that when the conversation turns to consciousness, some individuals may inwardly roll their eyes, thinking, "Oh, not this again." And it is true that a significant number of individuals, particularly within certain scientific disciplines, tend to deny the existence of a problem of consciousness, asserting that it is merely an emergent property of complex neural networks, fully explainable by physical processes. However, these individuals, though vocal, remain in the minority among philosophers and many scientists engage directly with these questions. For consciousness has been, and continues to be, one of the greatest enduring mysteries of science. To underscore its profound significance, consider a special issue of Science magazine published in 2005. This issue unveiled a list of 125 open questions in science, the grand challenges that stood before the scientific community. Can you guess which question secured the coveted first place? No, it wasn't a question about consciousness. The top spot was claimed by "What is the universe made of?" An absolutely deserved victor, given that, in the grand scheme of things, no one definitively knows what constitutes 96% of the matter and energy in our world, the elusive dark matter and dark energy. But the second place question, yes indeed it was, what is the biological basis of consciousness? This placement clearly signifies its status as a monumental, unresolved puzzle. So you undeniably know that you possess consciousness, this rich, internal, sensory experience. For you, the presence of your own self, your unique subjective world, is self-evident. The profound difficulty, however, lies in the fact that verifying the existence of consciousness in another human being is, by any known scientific method, utterly impossible. We have no objective instrument, no definitive biomarker, no foolproof test that can conclusively confirm the presence of subjective experience in another entity. This problem is not new. Over 400 years ago, the brilliant philosopher, physicist, and mathematician Gottfried Leibniz proposed a thought experiment that remains remarkably relevant today. He articulated it thus: it must be confessed that perception and what depends upon it is inexplicable by mechanical causes, that is, by figures and motions. And if we suppose there were a machine so constructed as to think, feel, and have perception, we could conceive of it as enlarged, while retaining the same proportions, so that we might enter into it as into a mill. And supposing this, we should find nothing but pieces working upon one another, but never anything by which to explain a perception. Leibniz was intimately familiar with mechanisms. He invented numerous devices, including a mechanical calculator that remained in use for 300 years until the advent of electronic computers. He believed that human logic could be accurately modeled and simulated by computational machines. Yet even with his profound understanding of mechanics and logic, he saw no conceivable way for a machine to generate subjective perceptions, the raw, qualitative experiences of consciousness. The eminent English biologist Thomas Huxley also grappled with the intractable mystery of consciousness. In 1869, he wrote, "That which is so wonderful as a state of consciousness should be the result of a disturbance of the nervous tissue is as inexplicable as the appearance of a jinn when Aladdin rubs his lamp." Huxley was an authority in anatomy and neuroanatomy. He meticulously compared the brains of humans and other primates, demonstrating the striking structural similarities that supported Darwin's theory of human evolution. Yet, despite his profound understanding of the brain's intricate architecture, he found nothing within its physical substance that could account for the generation of conscious experience. Even Sigmund Freud, the pioneer of psychoanalysis, found himself utterly bewildered by this chasm. He wrote, "One can speak of two aspects concerning what we call the psyche. Firstly, the bodily organ responsible for it, and secondly, the work of consciousness. Everything that lies in between is unknown to us, and contains no direct connection between these two extreme points of our knowledge. How and why something assembled from ordinary physical elements suddenly manifests subjective experience, a first-person perspective, remains as unresolved a question today as it was 400 years ago. Indeed, it's a question that likely surfaces in the minds of most ordinary people when confronted with the intricate, material reality of the human body. How can be this? This precisely is the explanatory gap. We lack a coherent, logical bridge from the purely physical system to the emergence of consciousness within it. And resolving this gap is not merely an academic exercise. Firstly, it would be profoundly helpful in situations where individuals find themselves in a persistent vegetative state following severe injuries. It is, to put it mildly, desirable to understand whether they are experiencing consciousness, whether they are aware of their surroundings, before making the deeply ethical decision to withdraw life support. Without a robust, empirically grounded theory of consciousness, such decisions remain agonizingly ambiguous. Secondly, and with increasing urgency, we are rapidly approaching an era where artificial intelligence and robotics will likely attain cognitive capacities comparable to, or even surpassing, human intelligence. How will we then determine whether these sophisticated machines possess subjective experience? Do we have a moral right to assemble and activate such a robot, only to later decommission or recycle it, if it is, in fact, a conscious entity? The core of the problem is that, despite robots being constructed from microchips and circuits, and we from flesh and blood, no known laws of physics fundamentally forbid the creation of identical mental states on vastly different physical systems. In simpler terms, it remains unclear why consciousness can be instantiated on a carbon-based substrate, as in humans, but could not, in principle, be realized on silicon, as in robots, or, for that matter, on any other suitable medium. Such mad possibilities are not entirely beyond the realm of theoretical contemplation. This concept is known as the argument for multiple realizability. It posits that a form of consciousness akin to your own could, potentially, be precisely replicated in a system that is as utterly distinct from your biological body as is conceivably possible. The idea of uploading consciousness into a computer, while a well-worn trope in science fiction, has unfortunately become so commonplace that it often fails to penetrate the deeper implications, the sheer radicality, of multiple realizability, if it were indeed a genuine feature of reality. To truly convey the profound, almost unsettling consequences of this idea, allow me to present a different, perhaps less hackneyed, example. The Soviet physicist Anatoly Dneprov, in 1961, proposed the first conceptual outline of an experiment now famously known as the Chinese brain, or Chinese nation, thought experiment. Its most widely recognized and elaborated form was described by the American philosopher of mind Ned Block in 1978. Without delving into all the intricate details, the essence of the experiment is as follows. Imagine the entire Chinese nation, then 500 million people, gathered together in an enormous field. The task assigned to each individual Chinese person is to simulate the function of a single neuron within a human brain. And crucially, they are to communicate with other neurons, other people, using telephones, in a strictly analogous manner to how neurons interact. In this system, each person would possess a telephone and a specific list of numbers of other individuals they are supposed to connect with. The entire nation of China would thus collectively emulate the complex, interconnected operations of a single human brain. Depending on when a particular Chinese person's phone rang, representing an incoming signal to a neuron, they would then, in turn, dial a number from their list, simulating the firing of that neuron. Crucially, the content of the phone message itself is irrelevant. It is merely the act of the call, the establishment of the connection that matters, mirroring the electrochemical interactions between biological neurons. According to a significant number of philosophers, such a colossal system, comprised of 500 million individuals, would, astonishingly, possess a unified, emergent consciousness. Just as an individual neuron in your brain does not, on its own, experience self-awareness, so too would no single Chinese person in this experiment feel conscious in that unified way. However, the entire system, as a coherent interacting whole, would experience a singular, unified subjective awareness. For instance, the Chinese brain might experience pain, even though no individual Chinese person within the system would feel that pain. One might immediately object, dismissing this thought experiment by arguing that such a system would be prohibitively slow and cumbersome, rendering it utterly dysfunctional, thus preventing any form of consciousness from emerging. However, Ned Block himself, the author of the experiment, writes that it is completely unclear why the temporal scale of the system should matter at all. The profound implication here is that the speed at which a system processes information may not be a defining characteristic for the asterisk existence of consciousness, merely for its speed of operation. Do you understand the profound philosophical schizophrenia this thought experiment reveals? Ned Block, in fact, originally devised this experiment precisely to demonstrate what he considered to be its inherent absurdity, to highlight the implausibility of consciousness arising in such a manner. Yet, as you can now grasp, many prominent thinkers disagreed with his conclusion. Daniel Dennett, one of the most celebrated philosophers of our time, in his influential book Consciousness Explained, argued that the Chinese brain could create any mental state that an ordinary human brain creates. And, ultimately, is it truly more intuitively obvious that a quivering mass of gray biological substance is a more fitting carrier of subjective experience than an enormous collective of individuals acting in a coordinated, unified endeavor? In matters concerning the exploration of the fundamental nature of the universe, it is highly perilous to rely on our intuitive judgments. Our intuition, throughout the entire sweep of human history, has proven to be a monstrously unreliable guide, frequently leading us astray. For instance, it is intuitively apparent to us that the Earth is flat and stationary. Yet, scientific inquiry has long since disproven these deeply ingrained intuitive perceptions. We simply do not know of any fundamental reasons why consciousness could not exist in such a distributed non-biological system as the Chinese brain, nor do we know of any fundamental reasons why consciousness could not exist elsewhere, in myriad other configurations of matter and energy. While the human brain remains the sole system definitively known to us that undeniably possesses consciousness, it would be remarkably imprudent and anthropocentric to declare, for example, that other animals lack consciousness in any form whatsoever. Indeed, it is highly improbable that consciousness functions as a simple on-off switch, a binary state of either present or absent. It is far more plausible that consciousness exists as a spectrum, a continuum of awareness, with some systems exhibiting a greater degree of consciousness than others, whatever that precisely might entail. If this spectral view is accurate, then some form of consciousness might extend to chimpanzees, to dogs, to pigeons, or even to lizards, and perhaps even to dragonflies, and so on, down the ladder of biological complexity. Where, precisely, does the boundary between conscious and unconscious systems lie? Is it at the level of humans and chimpanzees, or pigeons and lizards, or insects and bacteria? We simply do not know. No one possesses this definitive answer. However, we can, with a reasonable degree of confidence, assert that for something to possess subjective, felt experience, that something must be more than just a solitary electron. It must be a system possessing at least a minimal degree of size and complexity, for it requires some mechanism, however rudimentary, through which to process information and interact with its environment. If, from the lofty vantage point of our complex human consciousness, we struggle to comprehend even the potentially lower levels of consciousness ascribed, for instance, to animals, then how could we possibly grasp anything at all about forms of consciousness that are of a vastly higher order than our own? This is where the conversations late into the night with friends in the kitchen often begin to swirl. Does a state, a nation, possess a form of emergent consciousness? Does the global internet, with its billions of interconnected nodes and ceaseless flow of information, harbor a nascent awareness? Or, indeed, does the entire universe itself possess a form of distributed, overarching consciousness? Sabine Hossenfelder, in her customary precise manner, brings us back to the current scientific understanding. According to the currently established laws of nature, the universe cannot think. A clear, unambiguous statement, based on what we can presently verify. However, she then introduces a crucial caveat. However, physicists believe that the universe has many non-local connections, because this would solve several problems in existing theories. This is a speculative hypothesis. This refers back to the idea of microscopic wormholes or other non-local links that would bypass the speed of light constraint. But if it is correct, she continues, then the universe could possess enough fast communication channels to be conscious. Do you understand the profound logical trajectory here? All these seemingly mad reflections on the consciousness of the universe logically stem from our fundamental ignorance. We simply do not comprehend how subjective, felt experience, how qualia, arise from simple matter. And, perhaps even more fundamentally, why is it even necessary? What purpose does it serve for any system to be aware of its own existence? You might at this point object, arguing that consciousness is, in fact, absolutely indispensable for human beings to make informed, deliberate choices in various situations. If you are entertaining this thought, then I must gently inform you that it is precisely here that you have, perhaps unknowingly, stumbled into one of the most ancient and profound philosophical traps. Let us now shift our contemplative gaze into Chapter 3, Is a Human Just a Bag of Atoms? The very phrasing suggests a reductionist inquiry, stripping away layers of assumed complexity to reveal the fundamental constituents. Imagine, if you will, looking out upon the universe from the very instant of the Big Bang, tracing its grand unfolding narrative forward through time. In this cosmic epic, everything has evolved sequentially, meticulously. Each event, without exception, has been predicated upon a preceding event. Every consequence, in turn, has had its own discernible cause. To provide a vivid, illustrative mental image, one might envision the entire universe as a colossal billiard table, an infinitely vast expanse. Now, reflect upon the intricate chain reactions that unfold as billiard balls collide with one another. A ball cannot spontaneously begin to move, nor can it abruptly halt its trajectory without some preceding cause. A cue strike, an impact with another ball, the friction of the cloth eventually bringing it to rest. Therefore, every single movement of every single ball on this colossal table could, in principle, be calculated and predicted, both backward into the past and forward into the future, with absolute precision, given perfect information. This concept, the bedrock upon which our understanding of the physical world is built, is known as the principle of causal closure of the physical world. This principle asserts that every physical event has a purely physical cause. There are no gaps in the causal chain that require non-physical intervention. It lies at the very heart of the cosmos, because if cause and effect relationships did not exist, or if they could be arbitrarily violated, then the entire world would plunge into an unfathomable chaos. It would be akin to our billiard table analogy if the balls simply behaved arbitrarily, moving and stopping unpredictably, reacting capriciously upon collision, without any consistent laws governing their interactions. Such a world would be utterly incomprehensible, devoid of any discernible order. The world we inhabit, however, is not a chaotic free-for-all. It is a universe where the laws of physics are, for the most part, deterministic. This means that if you know the precise state of the universe at any given moment, the position and momentum of every particle, then, in principle, you could perfectly predict its future state and accurately deduce its past state. The current laws of nature, as presently understood, are largely deterministic, with one crucial, often debated, exception: the element of randomness inherent in quantum mechanics. This implies that the future is, to a significant extent, predetermined, save for the genuinely random quantum events upon which we, as macroscopic beings, have no discernible influence. As Sabine Hossenfelder articulates it, the currently established laws of nature are deterministic and contain an element of randomness from quantum mechanics. This means that the future is predetermined, with the exception of random quantum events that we cannot influence. So, returning to our initial question, what are you? A collection of 45 kilograms of oxygen, 12 kilograms of carbon, and so forth, remember? You are, in this scientific framework, a meticulously assembled collection of ordinary chemical elements, themselves composed of the most commonplace atoms. You are, in essence, a complex billiard ball, subject to the very same fundamental physical laws that govern everything else in the universe. And in the finest traditions of reductionism, the philosophical approach that seeks to understand complex systems by breaking them down into their simplest components, the logic unfolds. If we were to meticulously dissect your body down to its constituent atoms, if we were to ascertain the precise properties of each individual atom and understand how they interact with all other atoms, then, theoretically, we would be able to explain absolutely everything about how your brain and body function in their entirety. We would, in this grand vision, be able to predict, in advance, every decision you make, every action you undertake. Is this not, then, the inevitable conclusion? And if you are now feeling a familiar weariness, thinking, oh, for heaven's sake, not again with these discussions about the absence of human free will. Robert Sapolsky has already explained it all to everyone. It's old news. I would gently ask you not to rush to judgment. For Sabine Hossenfelder, a specialist in elementary particle physics, offers a nuanced, yet deeply challenging perspective. She writes, as a specialist in elementary particle physics, I must inform you that the available data indicate that the whole is the sum of its parts, no more and no less. This is a powerful, concise statement of reductionism. Countless experiments over millennia, she continues, have confirmed that objects are composed of smaller objects, and if you know what the smaller objects do, you can say what the larger objects do. There is no known exception to this rule. This empirical observation forms the bedrock of much of modern science. Yet, Hossenfelder, with her characteristic intellectual honesty, then adds a crucial qualifier. Nevertheless, I am not an advocate of reductionism. Our knowledge of the laws of nature is limited. Much remains to be understood, and reductionism may fail in some subtle aspects. This acknowledges the incompleteness of our current understanding, leaving open the door for unforeseen complexities. On one hand, if one truly grapples with the implications, the absence of free will seems almost self-evident, a logical consequence of a causally closed universe. To posit otherwise is to suggest that you are a chaotic billiard ball, somehow capable of defying the predictable forces that govern all other matter. And our perception that our decisions are free might simply be an illusion, a consequence of our inability to know the outcome of our deliberations before we have completed them. As Ludwig Wittgenstein, the influential philosopher, famously mused, "The freedom of the will consists in the fact that future actions cannot be known now." Our internal experience of choice, in this view, is simply the subjective experience of a complex deterministic calculation unfolding within our brains, the outcome of which is opaque to us until it has been computed. But what truly amazes Hossenfelder and many others is our profound, almost visceral resistance to the idea that we are merely biological marionettes. Humans not only fiercely believe in their capacity to make choices independent of any external factors, but we also exhibit a strong aversion to acknowledging any internal determinants, however subtle. For instance, the notion that human life is profoundly shaped by our genes is often met with discomfort, even outright hostility. One need only glance at the comments sections beneath videos discussing genetics to witness this instinctive pushback. Or consider the monumental explosion of indignation that erupted when Charles Darwin first formulated his theory of evolution. Darwin was ridiculed across the globe, not just by an uneducated populace, but by the most respected and educated individuals of his era. Caricatures depicting Darwin as an ape regularly adorned newspapers worldwide. The American evolutionary biologist and geneticist Jerry A. Coyne, in his book Why Evolution is True, remarked, "No scientific theory has aroused such anger and fear and such psychological resistance." The core of this resistance, then and now, often boils down to a profound existential discomfort. How can we be simply animals? For animals, then as now, were, and often still are, considered to be soulless biological robots. René Descartes, the celebrated philosopher, famously referred to animals as automata, arguing that while their external behavior might mimic human actions, their vital functions were merely the result of mechanical laws, the very same laws that govern the celestial bodies. Try in a casual discussion to suggest that humans possess instincts, and you will often be met with immediate, vigorous refutation, typically by individuals who themselves struggle to provide a clear, coherent definition of the term instinct. We are all deeply averse to the notion that we might be nothing more than unwitting puppets, devoid of genuine agency. But if, in the grand narrative of evolution, nothing occurs without a purpose, without a selective advantage, then what possible biological meaning or evolutionary utility could there be in our profound belief that we possess free will, and our ferocious defense of this idea? Hossenfelder notes with a touch of perplexity, "I have not heard a single convincing opinion on this matter." The question lingers. Why do we so desperately cling to this illusion, if indeed it is one? Our entire civilization, our intricate legal systems, our carefully constructed laws, our courts of justice, all of it is fundamentally predicated upon the unspoken, yet deeply ingrained, assumption that human beings possess free will. Whatever transgression an individual might commit, they will generally not be incarcerated if it can be demonstrably proven that they were not accountable for their actions. For instance, if they were acting in a state of profound mental incapacitation or temporary insanity. Robert Sapolsky, the renowned neurobiologist, controversially argues that we ought to abolish punishment for criminals, given the deterministic nature of our biology. "I say good luck to him," Hossenfelder might respond, expressing a realistic skepticism. It seems highly improbable that human society will ever permit such a radical shift, at least in part. Because yes, we profoundly believe that criminals possessed a choice. And, she adds, with a piercing observation, she wonders how many individuals who intellectually espouse Sapolsky's views would maintain their conviction if a crime were committed directly against them or their loved ones. I am not saying that they are wrong, she clarifies, speaking to the intellectual validity of the deterministic argument. I am saying that what people think they believe and what they actually believe are very often two very different things. We can intellectually deny free will as much as we desire, but the average person, in their daily actions and reactions, behaves as if they undeniably possess it. And, she reiterates, it is interesting that it is not obvious why this is necessary. Hossenfelder observes a recurring pattern. I found that many people reflexively reject the possibility that human consciousness arises from the interaction of many particles in their brain. They seem to adhere to the idea that there must be something else in consciousness. And, she adds with a precise understanding of human psychology, and although people with a scientific mindset do not call it a soul, that is exactly what they mean. They are looking for something mysterious, inexplicable, and amazing, something that would make their existence special. It's difficult to fault them for this innate human desire for meaning and uniqueness. Furthermore, Hossenfelder pushes the boundaries of this inquiry even further, provocatively stating that our entire biological shell could, in principle, be completely replaced by an artificial one. As far as we know at the moment, she asserts, the physical substrate of a being or object can be replaced by something else, as long as this replacement preserves the characteristic relationships and interactions. It must also maintain the functioning, including consciousness and identity. This is the philosophical core of what is sometimes referred to as the ghost in the shell concept. The idea that the underlying software of consciousness could run on different hardware. Consciousness, in this view, seems utterly unlike any physical process we currently understand. Its subjective, felt quality, its what it's like to be, seems fundamentally distinct from the objective, measurable properties of matter. It sounds, indeed, as though our consciousness might be something non-physical. But can there be anything truly non-physical in a universe governed by physical laws? The straightforward answer is, once again, we do not know. Because physicalism, the philosophical stance that everything that exists is fundamentally physical, is precisely that. A philosophical position, a metaphysical assumption, not an empirically verified scientific fact. However, if consciousness were indeed to possess some non-physical nature, then, as Sabine Hossenfelder astutely observes, in that case, it could not influence anything. Why? Because, according to the fundamental principle of the causal closure of the physical world, the very principle we discussed earlier regarding the billiard table, every cause of a physical event is solely and exclusively a physical event and nothing more. This is a long-standing, deeply challenging problem in philosophy of mind known as the problem of mental causation. If the mind is non-physical, how can it possibly exert any influence over the physical body? A non-physical entity, if such a thing were to exist, simply could not interact with the physical realm. To draw upon a popular cultural reference, Patrick Swayze's character in the movie Ghost would, in reality, never be able to interact with ordinary physical objects, however desperately he might try. Such an interaction would, in essence, rip apart the fabric of cause and effect relationships within the universe. To summarize the profound difficulty, if consciousness were truly as it appears to us, an irreducible, subjective experience that seems to defy purely physical explanation, it would inevitably give rise to a paradox. Can physics then resolve this deep paradox? this tension between our subjective experience and our objective understanding of the world. Lord Kelvin, the eminent physicist, famously wrote, "The power to direct the motions of matter, daily exhibited in the miracle of human free will, and in generations of plants grown from one seed, is infinitely different from any possible result of the accidental collision of atoms." While Kelvin was certainly mistaken about plants, the growth of a plant is indeed a complex, yet entirely understandable consequence of atomic interactions governed by physical and chemical laws. His intuition about free will perhaps touches upon a deeper, more intractable mystery. The simplest, most straightforward, albeit deeply unsatisfying, resolution is to assert that consciousness simply does not influence anything. Let us concede that it may seem to us 100 times over that our conscious choices genuinely drive our actions. But if that were the case, the question, what then is its purpose, remains profoundly open, an unanswered echo in the vast silence of the cosmos. A second, more complex, and equally speculative option to resolve the paradox of free will is the multiverse, or many worlds, interpretation of quantum mechanics. On one hand, the multiverse remains, for now, an ascientific hypothesis, intriguing, mathematically consistent, but currently beyond empirical verification. On the other hand, it's highly improbable that any act of conscious will could genuinely influence which particular universe you find yourself in. It would, most likely, remain a process strictly independent of your subjective awareness. However, if you are inclined to believe in the multiverse, and if the multiverse hypothesis were indeed to be a true description of reality, then you could, hypothetically, at this very moment, by your own will, literally and truly split universes. I have encountered this intriguing idea several times, discussed by theoretical physicists and cosmologists. And again, I've now read about this method in Sabine Hossenfelder's book. The underlying concept, stripping away any specific product mentions, involves a quantum device that, when faced with a binary choice you provide, e.g., choosing a blue or black shirt, would measure a single photon in a quantum superposition state. According to modern scientific understanding, that photon would simultaneously exist in both states, but in different universes. The measurement then reveals which branch of the universe you have entered. Thus, in another universe, you might be sitting here listening to this wearing a blue shirt, while in this one, you chose black. If the many worlds interpretation is indeed correct, this is not a mere jest. It's a profound, if mind-bending, implication. Now for the third, and perhaps most radical option in our discussion of the free will paradox. Let us reiterate that causality, the principle of cause and effect, is indeed a fundamental tenet upon which all known physics is built. However, it would be an overstatement to declare that a violation of cause and effect relationships within the universe is absolutely entirely impossible. Because, from the perspective of modern physics, there is, in fact, one extraordinary phenomenon that, quite plausibly, truly in time guys capable of tearing apart the very fabric of causal connections within the universe. I encountered this profound idea in George Musser's book, Spooky Action at a Distance, The Story of Quantum Entanglement, some of whose concepts I've touched upon previously in discussions about whether space truly exists. The question might seem deceptively simple, even foolish. What is space made of? This, one might say, is the apotheosis of reductionism, seeking the ultimate building blocks of the very medium in which everything else resides. But how would the fundamental constituents of space itself appear? Immediately, I must urge you to silence your intuition, for intuition invariably suggests that the building blocks of anything must be smaller than the object they form. Bricks, for instance, are always smaller than the house they construct. But here we are speaking of the fundamental, irreducible blocks of space itself. Therefore, concepts such as size and location simply cease to apply. These fundamental constituents would possess neither size nor position. They would, in a sense, be everywhere, permeating the entire universe, and yet nowhere, precisely because it is impossible to point to a place for them. As George Musser eloquently puts it, what does it mean for an entity to lack location? Where should they be? These are exceedingly complex questions, for which our everyday language simply lacks adequate words to formulate a satisfactory answer. And attempting to visualize such a concept is likely to lead to an immediate mental impasse. But this is not the central point I wish to convey. As George Musser writes, it may turn out that space itself is merely one state, and not just any state, but, drumroll if you will, a moment of dramatic pause, a very rare state of the universe. Most of the proposed theories of unified physics, theories that attempt to weave together all the fundamental forces and particles, suggest that the predominant, most natural state of the universe is non-spatial. The existence of space-time, as we experience it, is considered a remarkably atypical condition, requiring a very specific set of underlying circumstances. Rosalie C. Musser, a string theorist, offers a vivid, if rough, analogy. Consider water. Water can exist in various states, solid, liquid, and gaseous, even though its fundamental building blocks, the water molecules, remain identical. The gaseous state, steam, is one where the interactions between these building blocks achieve a monstrous complexity, as they exist in a state of absolute, continuous chaos. You can witness this chaos by observing the steam billowing from a boiling kettle. In contrast, in its solid, icy state, the water molecules exhibit a profound simplicity arranged in an ordered, sequential lattice. But the underlying complexity never truly vanishes. It merely recedes, waiting for its opportune moment. And given that water exists in its solid state, within a far narrower range of conditions than in its gaseous state, at any moment, given the right conditions, that chaos can erupt, and the ice will begin to evaporate. The same, Musser suggests, may be true for space itself. The fundamental building blocks of space, throughout the vast majority of the universe, may typically exist in a chaotic, non-spatial state. But in rare instances, as a result of incredibly intricate and precise interactions, they can coalesce to form a simple, ordered lattice. This is a mind-boggling thought. An incomprehensibly complex network of interactions contracts down to a few numbers that we call position and time. This, George Musser argues, is what we refer to as the Big Bang. It was the moment when the universe, in a sense, emerged from a primordial chaos that, by chance, adopted a sequential, spatial structure. However, just as in the analogy of the melting ice, the underlying complexity and unimaginable chaos never truly vanish. They remain, ever present, awaiting their moment. Even when the system is spatial, a vast amount of hidden complexity persists. The universe we see as unfolding in space, Musser suggests, may be merely a surface where we float like small boats, while monstrosities churn in the depths. At any moment, this latent chaos can erupt. The very building blocks that constitute our causally coherent space can, like melting ice, lose their ordered arrangement and revert to a non-spatial structure. And this, he claims, is precisely what occurs ubiquitously throughout the cosmos. This is what we call black holes. Within these enigmatic objects, the system of fundamental blocks that form space-time loses the simplicity of its ordered structure. Space, quite literally, disintegrates. And events within black holes lose their distinct position and their progression through time. This implies that black holes might be regions where the fundamental building blocks of space have reverted to their more natural, chaotic, non-spatial state. This profound shift leads to an astonishing consequence. All cause and effect relationships within black holes are shattered. To illustrate, if you were to write the equations describing the motion of an object falling into a black hole, the moment that object reaches the singularity at its core, the equations simply cease to function. They can no longer predict what will happen next. And this is why, at the beginning of the Big Bang, there was a singularity, and within black holes, too, resides a singularity. A singularity, in this context, is a point where the known laws of physics transition into unpredictable chaos. Thus, the seemingly unbreakable rule of cause and effect relationships does, at least theoretically, possess an exception. But there's another fascinating aspect to this example, one that beautifully illustrates a deeper principle. Individual atoms of hydrogen and oxygen are not wet. They possess none of the properties we associate with water. Yet, when they combine in the specific ratio and bonding of H2O, they form water, a substance with entirely new, emergent properties, such as wetness, that cannot be found in its constituent atoms. In precisely the same way, space, in this view, is formed from elements that are themselves non-spatial. This phenomenon is called emergence, a concept where the properties of a system cannot be simply reduced to or predicted from the properties of the individual blocks or components that make up that system. When we contemplate the emergence of time, for instance, it must arise from some basic structure that is very far from what we are familiar with, as Nima Arkani Hamed, another prominent string theorist, suggests. In essence, much of what we perceive around us is emergent. It is a complex interplay of various atoms, molecules, and larger structures. This might sound overly abstract, but in reality, the concept is quite straightforward. If you meticulously arrange atoms into the specific configuration of a cat and imbue them with the correct kinetic energy and interactions, that cat will, indeed, come to life. No magical wand-waving is required. However, each of those individual atoms, taken in isolation, does not possess the properties of the whole cat. An individual atom, for instance, cannot purr. Therefore, a cat, in its entirety, is an emergent phenomenon. And everything we currently understand about the laws of the universe strongly suggests that only a weak form of emergence exists. This means that while we may not be able to, for instance, directly deduce the laws of animal behavior from the fundamental laws governing elementary particles, it doesn't imply that such a deduction is fundamentally impossible. It simply means that our current computational power and understanding are insufficient to perform such a complex derivation. All of this operates strictly within the framework of reductionism, where all cause and effect relationships flow rigorously bottom-up, from the constituent building blocks to the larger structures they form, from the atoms to your brain, which is, in its essence, composed of those very same atoms. However, scientists and philosophers are engaged in an ongoing, lively debate regarding the existence of strong emergence. Strong emergence posits the existence of fundamentally novel phenomena that cannot, in principle, be predicted or explained, regardless of how much we understand about the underlying processes or components. This is a more radical form of emergence, where the resulting properties or behaviors are not merely surprising but genuinely inexplicable from the perspective of the system's components. In essence, strong emergence would fundamentally challenge reductionism, asserting, quite literally, that The whole is not equal to the sum of its parts. The profound challenge here is that we have yet to discover a single instance in the world that unequivocally demonstrates the property of strong emergence. If one were to conclusively prove the falsity of reductionism, one would need to demonstrate that a description of a system in macroscopic terms leads to predictions that are demonstrably different from those derived from its microscopic description. No one, to date, has successfully achieved this. Again, this is not because it is necessarily impossible in principle. Rather, it speaks to the profound difficulty of finding such a case, or perhaps to its absence. You might attempt to imagine a world where the behavior of atoms is dependent on the behavior of planets, rather than the other way around. But, as far as we can discern, that simply is not the case. Fundamentally, the problem is that, as far as our current knowledge extends, strong emergence appears to be impossible. Sabine Hossenfelder, in her customary direct style, would assert that strong emergence sounds like absolute nonsense, like magic. Because, imagine this, you meticulously assemble a robot, programming it to execute a specific set of actions. And then, suddenly, this agglomeration of plastic and silicon, without any discernible cause or reason, ceases to follow its embedded algorithms. It informs you, with an eerie, self-possessed certainty, that it possesses feelings, and proceeds to behave in a completely unpredictable manner. Yes, I believe you have now grasped the profound suspicion, the deep-seated intuition that many hold. Human consciousness, which appears to emerge from the irritation of nervous tissue, is not easily derivable from known physics. Indeed, it is not even clear, in principle, how it could be derived from purely physical processes. While the brain is undeniably composed of neurons, its conscious, subjective experience cannot be fully explained simply by knowing the activity of those neurons. This is a profoundly strange property of matter, one whose nature is so obscure that it has led people to propose ideas as radical as the entire universe possessing consciousness. You heard this earlier. Therefore, many thinkers advance the hypothesis that consciousness is, quite possibly, the first known candidate for strong emergence. What, then, is the ultimate conclusion we can draw from this intricate tapestry of ideas? Using the laws of physics, it is, in principle, possible to link every choice we make to the distribution of matter at the dawn of time. This, however, does not necessarily mean that your will is not free. Freedom, in this context, could be an emergent property, a quality not possessed by individual particles, but by a complex system of particles. As for you, your choices may be absolutely free until you make them. Nevertheless, philosophers, scientists, and students, engaged in late-night conversations, continue to vigorously debate this profound topic. As Philip Warren Anderson, the Nobel laureate in physics in 1977, famously stated, "More is different." Recall the widely publicized experiment conducted by neurobiologist Benjamin Libet, which seemed to reveal a profound challenge to the notion of free will. His research indicated that electrical activity in the brain of a subject could be detected several hundred milliseconds before the person consciously became aware of making a decision. This suggested that one could predict a person's choice even before they themselves consciously registered having made it. This, it was argued, proved that we lack free will, because the brain apparently makes the decision first, and only then communicates it to our conscious awareness. Robert Sapolsky frequently cited this experiment as compelling evidence for determinism. Yet, with all due respect to Robert Sapolsky, and irrespective of whether free will ultimately exists or not, I have always found it difficult to understand how this experiment necessarily leads to the conclusion of an absence of free will. For instance, neurobiologist Kevin Mitchell, in his book Free Agents: How Evolution Gave Us Free Will, writes, There is this idea that if some mechanism within the brain activates when we make a decision, it supposedly follows that decision-making is nothing more than the action of that mechanism. I don't think that's the right point of view. It seems to me that it only follows that to make decisions we need to use some biological mechanism. Mitchell argues that our biology, through billions of years of evolution, has shaped us into free agents. This, he contends, represents, quote, an entirely different type of causality than anything previously observed in the universe. And, astonishingly, Benjamin Libet himself, the very author of the groundbreaking experiment, towards the end of his life, came to a rather different conclusion. He ultimately believed that consciousness is not merely a product of brain activity. He formulated what he called the conscious mental field theory, positing that this field could freely act on many neural functions, thereby, after all, enabling free will. Whatever our individual assessment of this hypothesis, however strange it might appear, it at least demonstrates, unequivocally, that discussions concerning consciousness and free will are, to put it mildly, far from concluded. But what, then, is Sabine Hossenfelder's ultimate perspective on this enduring enigma? She states that she personally believes there is no free will, yet she readily allows for the probability of its existence. The only way in which free will would make sense, she posits, is if the derivation from the microscopic theory fails in some cases for some reason. This points directly to the concept of strong emergence. Then, strong emergence could become a real property of nature, she continues, and we could observe macroscopic phenomena, including free will, which are genuinely independent of the microscopic input. This would imply a singularity, a boundary beyond which we simply could not penetrate, either in practice or in principle, when trying to understand the macroscopic from the microscopic. Currently, we have no reason to believe that this happens in our actual universe, she concedes. But it might turn out to be the case when we better understand the mathematics. Her final synthesis on this profound topic is as follows. So, if you want to believe in free will that is genuinely governed by laws of nature independent of the laws of elementary particles, then the possibility that the derivation of macrophytes leads to a singularity seems most reasonable to me. It's improbable, but it's compatible with everything we currently know. There is a certain beauty, a poetic resonance in this thought, that just as black holes are embodiments of chaos, so too, perhaps, are human beings. No one truly knows what transpires within their deepest interiors. Yet, paradoxically, I must confess that I am not particularly enthusiastic about the prospect of our will truly being free. For if one were to seriously contemplate the immense, crushing weight of responsibility for every single conscious choice throughout our entire lives, the mind begins to reel, almost dizzy with the burden. This leads us to a profound philosophical concept, causa sui. Translated from Latin, it means, quote, cause of itself. In the context of many religious and philosophical traditions, this term is used to describe God, for only God is considered to be dependent on nothing else, being the ultimate source of existence. And it is precisely this capacity to make free choices, to be the uncaused first cause of one's own actions, that, according to many influential religious traditions, God has bestowed upon humanity, creating us in a likeness to the divine. Let us now, with a gentle transition, move into Chapter 4, Does the Universe Have a Creator? I believe that if you have been following our contemplative journey thus far, you would likely have long since surmised Sabine Hossenfelder's particular religious inclination. She is an agnostic. In simple terms, an agnostic is someone who believes that because we are inherently incapable of directly perceiving or fully comprehending the surrounding world, being limited to our sensory organs and our own finite minds. We can therefore never confidently assert anything definitive regarding the existence or non-existence of God, or indeed of any gods. There simply isn't enough information, or perhaps the right kind of information, accessible to us. Yet, concurrently, Hossenfelder has also candidly stated that it would be remarkably simple to convince her of God's existence. God would merely need to descend from the heavens and perform some undeniable miracles. And upon hearing this, I found myself pondering, why precisely would this constitute proof of God's existence? Because, to recall a fundamental principle, Arthur C. Clarke's third law states, any sufficiently advanced technology is indistinguishable from magic. How, then, could we definitively know that we were witnessing the hand of God, rather than, say, the elaborate deception of an incredibly advanced alien civilization manipulating our perceptions? Or how could we be certain that we weren't merely trapped within a sophisticated simulation that had temporarily glitched? Or, indeed, how could we know in the end that we hadn't simply irrevocably lost our minds? In short, one could conjure a million alternative explanations, none of which could be 100% excluded. This is precisely the core of agnosticism. Human capacity for knowledge possesses inherent, insurmountable limitations. Sometimes, Hossenfelder reflects, the only scientific answer we can give is, we don't know. Therefore, she finds it highly probable that in our continuous process of discovering knowledge, religion and science will continue to coexist for a very long time. This is not an indictment of either, but a recognition of their distinct domains and inherent limitations. This is because science itself is limited, she explains, and where science ends, we seek other ways of explanation. Crucially, Hossenfelder makes a clear distinction. Science, as a useful way of describing the world, does not exclude the existence of a creator, but it also does not require its existence. This is a statement of intellectual neutrality, a refusal to overstep the boundaries of scientific inquiry. It's not that I want to be polite to religious people just for the sake of being polite, she clarifies with characteristic bluntness. Let's start with the fact that I'm not exactly known for my politeness. But, she continues, more importantly, scientists who claim, like Stephen Hawking, that the existence of a creator is impossible, or, like Victor Stenger, that God is falsifiable, demonstrate that they do not understand the limits of their own knowledge. She expresses a profound discomfort. When prominent scientists make such overconfident statements, it makes me cringe. It is a reminder that even the most brilliant minds can occasionally stray beyond their domain of expertise, particularly when venturing into metaphysical territory. If we set aside the specific dogmas of any particular religion and simply contemplate the concept of God in its most general, universal, humanistic terms, as an omnipotent, omniscient, benevolent creator, it seems to me that if we were to somehow definitively discover that such an almighty God truly existed, it is highly improbable that we would find this revelation comforting or even pleasant. On the contrary, we would instantly grasp that we were, in fact, living in an utterly unpredictable, profoundly chaotic world, a world where there exists an unknown agent, an entity possessing absolute free will and infinite power, with the capacity to do literally anything our imaginations could conceive, and perhaps even more terrifyingly, things our imaginations could not conceive. Compared to this, even the most colossal black holes would seem like mere child's play, simple, predictable entities. It would be entirely unclear why such a God would necessarily conform to human notions of goodness or justice. Why would a being of infinite power be constrained by the moral frameworks we, as finite beings, have developed? At the very least, we would find this unsettling because, as I touched upon earlier when discussing Hume's problem of induction, Our very nature recoils from anything associated with dangerous uncertainty. This inherent aversion to unpredictability manifests in every aspect of our lives. From the seemingly trivial, like feeling an inexplicable urge to check the second unopened room in your hotel suite, no matter how exhausted you are upon checking in, to the profound, such as our zealous fanatical drive to uncover all the underlying laws that govern the universe. We are, undeniably, the most curious species on the planet. And what, fundamentally, is curiosity, if not a sophisticated form of defense against the unpredictable? Throughout human history, we have ceaselessly striven to render our surrounding environment predictable and safe. We have ventured across oceans to discover new continents, plunged into the crushing depths of the ocean, and devised ingenious methods to peer into the most remote corners of the cosmos. Our entire intellectual endeavor is a grand project of prediction and control. But a God, an entity of fundamental unknowability, a principle of infinite power, this would introduce an element of pure, irreducible unpredictability into the very fabric of existence. And the situation becomes even more complex, potentially even worse, if God were indeed to resemble us in some fundamental way, or if we were made in God's image. Because, once again, it is far from obvious why such a being would necessarily be good or just. Our crew consistently good and just. As Niccolò Machiavelli wrote in his seminal treatise, The Prince, a text often considered the quintessential manual for effective, albeit sometimes ruthless, rulers. Men are always bad unless necessity makes them good. What force, then, could possibly compel an omnipotent being towards goodness? There is, in fact, a film that, in some profound way, explores this very theme, the unsettling implications of suddenly discovering the existence of a being who is, in essence, godlike, and who also happens to resemble us. And you might be surprised to learn which film I am referring to. It is a being capable of annihilating the entire human race. And if there is even the slightest probability that this being is our enemy, then, by extension, it all store is our enemy, and it must be destroyed. Yes, I am speaking of Batman v Superman: Dawn of Justice. In this film, Bruce Wayne, Batman, adamantly insists that Superman must be eliminated, precisely because he is too powerful and, critically, possesses free will. He is, therefore, inherently unpredictable, even though Superman is, at that moment, unequivocally not humanity's enemy. Bruce Wayne's chilling pronouncement, "but he could be," speaks directly to the core of human nature. Through the voice of Bruce Wayne, at that pivotal moment, speaks the entirety of human experience. Throughout our history, we have methodically destroyed, or tirelessly attempted to destroy, anything and everything that presents an existential threat to us. Carthage must be destroyed is not merely an ancient Roman refrain, but a psychological imperative for survival. The film's director, Zack Snyder, raises a truly deep and compelling question. What if God were real? Are our cherished preconceptions about the divine truly accurate? Are we not, in fact, projecting onto this concept the very qualities we desperately wish to see? And what fate awaits us if, in an unexpected turn, it should transpire that God, much like ourselves, is far from perfect, perhaps flawed, unpredictable, or even indifferent? And science, in its dispassionate analysis, suggests that the latter possibility could, indeed, be entirely true. If the universe does possess a creator, that creator could very well be as imperfect, as flawed, as we ourselves are. Theoretical physics, with its audacious scope, even suggests that if we were to take something not particularly massive, say a standard computer chair, extract all the energy contained within the atoms that compose it, and concentrate that energy within a minuscule region of space, we would, in all likelihood, instantly become gods, in the most literal sense of the word. In the most literal sense of the word, Alan Guth, André Linde, and many other eminent physicists have demonstrated that creating a new universe requires a finite, quantifiable amount of energy. According to the most optimistic estimations, the creation of an entirely new universe would require approximately 10 kilograms of pure energy. Sabine Hossenfelder acknowledges that this is, of course, extremely far from our current technologies. We are not yet capable of such feats. But theory, she asserts, says there are no fundamental limitations to this. And she adds, it's possible that one day we will be able to create a new universe in a laboratory. Such a nascent universe would then grow and separate from our own, much like a drop of water detaching from a faucet. From the perspective of the newborn universe, she describes, it would briefly resemble a tiny black hole. It would disappear in a fraction of a second. And, with a touch of cosmic melancholy, she adds, we would never know if there were inhabitants there and what happened to them. This nascent universe, she explains, would not be destroyed. Rather, it would simply and very rapidly expand into its own self-contained space-time, effectively becoming its own cosmos. Crucially, the fundamental physical constants of this newly created universe, the precise values that dictate the laws of physics within it, would depend entirely on the specific combination of pressure, temperature, and the tension of the inflaton field that the Creator chose. One could, theoretically, engineer a universe with precisely the most favorable conditions for the emergence of intelligent life. Some cosmologists, in fact, even hypothesize that our own universe may have originated in precisely this manner, a cosmic experiment by an advanced intelligence. Listen to the words of the Russian-American physicist André Linde, renowned globally as one of the primary architects of the theory of the inflationary universe, as well as the theory of eternal inflation and the inflationary multiverse. If I wanted to send a message to the inhabitants of a universe I created, I would record it in the local laws of physics. He further elaborates on the complexity of such an endeavor, and to transmit a long and meaningful message, I would have to make these laws sufficiently complex. For example, I would have to ensure that the masses of the electron, proton, and neutron were in non-trivial ratios, the deciphering of which would become a serious task for future physicists. Therefore, it is not beyond the realm of possibility that we, without even realizing it, are currently engaged in a profound act of decipherment, attempting to unravel a hidden message from the superintelligent, albeit by no means divine, creators of our world. Sabine Hossenfelder further expanded on these profound, introspective discussions through her interviews with Zia Morali, a physicist who frequently contributes to prestigious scientific journals such as Scientific American, Science Scientist, Science Scientist, Science Mine, Weorka, Minate, Science Nature, and collaborates with media outlets like the BBC and Novaya Gazeta on science reporting. In 2017, Zia Morali published her own compelling book titled A Big Bang in a Little Room, which explores the fervent ambition of physicists to understand how to create a universe and whether humanity might one day achieve such an astonishing feat. Morali recounted her experience interviewing various prominent physicists for her book. To her considerable surprise, these brilliant minds spoke with remarkable candor, not only about the intricacies of physics, but also about their deeply personal philosophical reflections on these very topics. What surprised me, she confessed, was how much they had thought about these questions. Questions such as, if we can create a universe, could our universe also have had a creator? And other oblique, yet profound, inquiries that they serendipitously encountered during their studies of cosmology, quantum foundations, or even quantum gravity. Questions like, does the universe require consciousness? Are we part of a larger field of consciousness that encompasses us all? Do we possess free will? André Linde, the cosmologist, also pondered whether the cosmos must necessarily be observed by some kind of superknowledge, or merely by an inanimate recording device, for time within the universe to even begin ticking. These deeply philosophical ideas, he revealed, first germinated in his mind while he was contemplating the mysteries of quantum gravity and the early universe. Alex Vilenkin, another physicist known for demonstrating how the universe could have been created from nothing through a quantum fluctuation, clarified that by nothing, he meant the absence of space-time and matter. Yet even Vilenkin was curious about how the quantum laws themselves came into existence. So in essence, it wasn't truly nothing in the absolute sense. The foundational physics and mathematics were still implicitly present, merely highlighted the deeply human aspect of these exchanges. Scientists spoke very personal things, expressed bewilderment, and confessed that sometimes they didn't always know what to think. She found this particularly compelling. What I found interesting was that these people are incredibly meticulous about physics, but then they can be very emotional and philosophize freely, just like any of us. They have the same questions and uncertainties. They don't know the answers to all questions, and they are fully prepared to admit it. She genuinely desired to convey this vulnerability, this intellectual humility, in her book. Because as I see it, she mused, people have the impression that science closes many questions. But these people would say, I don't have an answer to that, and they were humble about it. I wanted to convey that to the public. Now, let us bring our contemplative journey to a close with a final resonant image. In the expansive public square opposite the British National Library, one of the largest and most revered libraries in the world, stands a monumental bronze sculpture. Poised on a tall plinth, this striking work, authored by Edoardo Paolozzi, is simply titled Newton. And, quite explicitly, this sculpture directly references and draws inspiration from the iconic engraving by William Blake, which we discussed earlier. Considering Blake's profound antipathy towards Isaac Newton and, more broadly, his critique of the reductionist scientific approach, one might naturally wonder, is this not perhaps the most incongruous, indeed the worst, possible monument to erect in the public square of one of the greatest repositories of scientific knowledge? A depiction of Newton that Blake intended as a critique, a symbol of reductionist blindness. I, however, propose a different interpretation, one infused with deep symbolism and a profound message. I believe that the bronze statue of Newton, in this context, stands as a quiet, yet powerful reminder to all who visit the library. It whispers that while the human intellect, with its rigorous scientific methods, is an astonishingly potent instrument for unraveling the mysteries of reality, no true or complete scientific understanding of the universe will ever be possible if we remain willfully blind to the inherent limitations of that very instrument. The deeper symbolism, the profound message embedded in this artistic choice, suggests that the world, in its bewildering grandeur, is ultimately something more than merely the sum of our current representations and scientific descriptions of it. And we, in our own unfathomable complexity, are also something more than just the aggregate sum of the atoms that constitute our physical form. We are the conscious observers, the curious questioners, forever suspended between the known and the unknowable, drawn by an irresistible urge to comprehend the universe and our place within its unfolding narrative. Thank you for sharing this contemplative journey. May your mind be filled with quiet wonder, and may you drift into a deep, restorative sleep.